Next example, let x1, x2 and so on be a sequence of random variables, each having CDF cumulative distribution function f suffix x n of x, it is 0 from minus infinity to 0, and it takes a value 1 minus x by n power n for x is lies between 0 to n. From n onwards till infinity, the value is 1. So, this is the cumulative distribution function for the random variables xi's. It is a function of n, therefore, I have made it a f suffix x suffix n. That means, this is a CDF for the random variable n. For every n, you have this form. As n tends to infinity, we get f suffix x n of x that becomes 0 from minus infinity to 0, and it takes a value 1 minus e power minus x from 0 to infinity. As n tends to infinity, the CDF of the random variables x n becomes 0 between the interval minus infinity to 0, and the value becomes 1 minus e power minus lambda x, where x is lies between 0 to infinity. Suppose x is a random variable with the CDF that is f x of x, that is 0 between the interval minus infinity to 0 and 1 minus e power minus x, where x is lies between 0 to infinity, then one can conclude x n converges to x in distribution, since the sequence of f x suffix n of x tends to f of x for x is greater than or equal to 0, and the value is 1 minus e power minus x. Hence, one can conclude the sequence of random variable x n converges to the random variable x in distribution. Here the x is a exponential distribution with the parameter 1. So, this is the one example of how the sequence of random variable converges to a random variable in distribution. Next, I will move into the third example. Suppose we choose at random n numbers from the interval zero to 1 with the uniform distribution let capital X I be a random variable describing the ith choice. then for I is equal to 1, 2 and so on, you can find out what is the expectation of xi's, that is nothing but the integration from 0 to 1 x times the probability density function. The probability density function for uniform distribution with the interval 0 to 1, that is 1. Therefore, x into dx, if you compute, the expectation of xi is going to be 1 by 2. Similarly, one can evaluate the variance of xi's, that is nothing but the 0 to 1 x square dx minus the mean square, expectation of x square minus expectation of x whole square. So, the expectation of x square is 0 to 1 x square dx. So, if you evaluate this quantity, that is 1 by 3 minus 1 by 4. So, if you simplify, you will get 1 by 12. If you remember the formula of variance of a uniformly distributed random variable between the interval a to b, then the variance of x is nothing but you can get it by substituting the value of a is equal to 0 and b is equal to 1, you will get 1 by 12. Let s suffix n be x1 plus x2 and so on till xn. One can find mean and variance of Sn, because you know the mean and variance of xi's. Using that, you can find out what is the mean of Sn, but our interest is not the finding the mean of Sn, our interest is to find out the mean of Sn by n. That is basically, suppose xi's are the samples, then Sn divided by n is nothing but the sample mean. So, expectation of Sn divided by n, that becomes 1 by 2. Similarly, if you calculate variance of Sn by n, that becomes 1 divided by 12 times n, because the variance of xi's is 1 by 12. So, the variance of Sn is a summation of xi's from 1 to n. Therefore, variance of Sn by n becomes 1 divided by 12 times n. For any epsilon greater than 0, using Chebyshev inequality, one can conclude the probability of absolute of Sn by n minus 1 by 2 greater than or equal to epsilon, that is less than or equal to 1 divided by 12 times n epsilon square. I am using the Chebyshev inequality by knowing mean of Sn by n is 1 by 2 and variance of Sn by n is 1 divided by 12 n. I get this inequality. Now, as n tends to infinity, the probability of absolute of Sn by n minus 1 by 2, which is greater than or equal to epsilon, will tends to 0, because epsilon is in the n is in the denominator, because n is in the denominator. As n tends to infinity, this probability tends to 0. That is nothing but Sn by n tends to the value 1 by 2, and this convergence takes place in probability. This sequence of random variable Sn by n converges to 1 by 2 in probability. Therefore, we say the sequence of random variable x n for n is equal to 1, 2 and so on obeys the weak law of large numbers, because the S n by n converges to 1 by 2 in probability. Therefore, we say the sequence of random variables say x n's obeys the weak law of large numbers. So, that is the intention of giving this example.